Okay, our new unit, which includes chapters 10 and 11 in your book, is all about thermochemistry, and as you can probably imagine, that has to do with heat. So we're going to be looking at heat changes that occur during chemical reactions or physical changes. That's what thermochemistry is concerned with. And what's really happening is we're looking at energy. Energy is the capacity for doing work or supplying heat. And specifically, in a chemical reaction, we're looking at the chemical potential energy, which is stored within the structural units of chemical substances. We already looked at this a little bit when we did combustion reactions, and we talked about the bond energy, the energy that's stored within the bonds, and when they're broken or when they're made, what that tells us about the reaction. So that's part of thermochemistry. Okay, now when we are in thermochemistry, we're worried about heat, and heat is energy that transfers from one object to another because of a temperature difference between them. Heat is always going to be transferred from higher temperature to lower temperature. Now, heat is not something we can detect. You can't measure heat, okay, but you can measure what heat changes, like you could measure a change in temperature with a thermometer. We are going to use delta H to represent heat. That delta, that triangle, is a Greek letter. It's the Greek letter delta, and it means change in. So anytime you see that delta right there, it means change in. So delta H means change in heat. We also use the term enthalpy, which is heat at constant pressure. So heat and enthalpy, delta H, they're interchangeable with each other. Now, when we talk about heat being transferred, we need to define what is being looked at, basically. So we want to define the system as the part of the universe on which you focus your attention, and the surroundings as everything else. Okay, so let's look at this flask, and there is some sort of contents going on in the flask. We could define that stuff in the flask as the system. We might even define the flask as the system. Everything else around it is considered the surroundings. So the air around it, the table around it, we are part of the surroundings. When you touch something, you are part of the surroundings. So we have to focus on what's going on in the system in terms of heat transfer. So when we are looking at heat transfer, we want to make sure we're following the law of conservation of energy, which says that in any chemical or physical process, heat is neither created nor destroyed. It's conserved. So if a system loses energy, then that energy is gained by the surroundings. Or if a system is gaining energy, then it had to have been lost from the surroundings. It doesn't just come from nowhere. So we can define these processes as either endothermic or exothermic depending on the direction of the heat flow. So if a process is exothermic, that means the system loses energy and the surrounding gains energy. So as part of the surroundings, we would feel warmer. If you were to touch a beaker and it feels warm, that means the system is losing energy to the surroundings, and that's an exothermic process. We could also show the value of delta H to be negative because the system is losing that amount of energy, and the energy would be considered a product in that particular reaction. If a process is endothermic, that means the system is gaining energy, and that energy is coming from the surroundings. So the surroundings are actually going to feel cooler. When you touch something and it feels cold, you're actually feeling heat from your hand being lost into that thing. So as part of the surroundings, you're losing energy and it feels cold. So the delta H would have a positive value because the system is gaining energy, and we could think about the energy as a reactant in that particular equation. Okay, now what are the units of heat? Well, there are several. We will use the calorie or the joule. Those are the two main units that we will use. A calorie is defined as the quantity of heat needed to raise the temperature of 1 gram of pure water 1 degree Celsius. Now, when you think of calories, you're actually thinking about capital C calories, which refers to energy stored in food. And actually, a capital C calorie is equal to 1,000 little calories. So a capital C calorie is a kilocalorie. We will also use joules. Joules is actually the scientific unit for heat, and it has the equality that 4.18 joules equals 1 calorie. So this is going to be a new conversion factor that we can use to convert between units. So, for example, we want to convert 161 joules to calories. So using dimensional analysis, we would start with 161 joules, capital J, over 1. And then our conversion factor says that 1 calorie is equal to 4.18 joules. So our joules cancel. And when you divide, you get 38.5 calories using our 3 sig figs that we had to begin with. So you will need to know that conversion factor to get from calories to joules or joules to calories. Okay, now the next thing we're going to look at is called the specific heat of a substance. And the specific heat is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. And it's a property of that substance. It's like the density or the melting point or the boiling point. And it's actually in your textbook on page 296, there's a chart of specific heats of different substances. Now this formula right here is how we relate heat to specific heat. Specific heat is this capital C right here. So in our formula, delta H equals Cm delta T. Delta H is our heat in joules, C is the specific heat, and the units are joules per gram degree Celsius. The little m is mass in grams, and the delta T, change in temperature, is found by taking the final temperature minus the initial temperature. So the heat in a process is equal to the specific heat times the mass times the change in temperature. Okay, so let's look at an example using our new formula. So delta H equals Cm delta T. All right, the temperature of a piece of copper with a mass of 95.4 grams increases from 25.0 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. What is the specific heat of copper? So we want to solve for the specific heat. So if we rearrange our formula, then the specific heat will equal delta H divided by m delta T. Okay, so the heat involved is 849 joules divided by the mass of the copper, which is 95.4 grams, times the change in temperature. And for the change in temperature, we take 48, which is the final temperature, minus 25, which is the initial temperature, and that's 23.0 degrees Celsius for our change in temperature. So when we divide, we get 0.387. Now our units are joules per gram degree Celsius. So the specific heat of copper is 0.387 joules per gram degree Celsius, and we can always check the table in the book to make sure that we are correct, because that should be a property of that element, copper.